Tonight, we're going to explore one of the most seductive promises in modern science. For decades, we've been told that Mars is humanity's future, a second home, a backup planet, the place our civilization will expand to once Earth is no longer enough. And somehow, that future has begun to feel inevitable. After all, we've crossed oceans, climbed mountains, flown across continents, and walked on the moon. Every generation has gone farther than the one before it. Give us a bigger rocket, stronger radiation shielding, enough money, and enough time, and surely Mars becomes just another frontier waiting to be crossed. So why should Mars be any different? Because Mars may not be separated from us by a problem engineering can eventually solve. It may be separated from us by limits that technology can reduce, but never fully remove. Consider the journey alone. A round trip could expose an astronaut to roughly 660 millisieverts of radiation, comparable to receiving a full-body CT scan every 5 days for a year and a half. And that is before years spent beneath a thin Martian atmosphere, with no global magnetic field shielding the surface from space. Then, there is the distance. If something goes wrong, there is no rescue mission waiting nearby, no immediate medical evacuation. Even a message from Earth can take up to 20 minutes to arrive, and the next practical opportunity to come home may be years away. That is the part the dream rarely shows. The real question isn't whether we could send a handful of astronauts to Mars and plant a flag. With enough effort, perhaps we could. The question is whether Mars could ever become what we've been promised. A survivable, repeatable, permanent second home for human civilization. Because when you look beyond the rockets and follow the physics, the biology, and the arithmetic of the journey, the future begins to look very different. The farther you follow the numbers, the less inevitable Mars becomes. By the end of tonight, you'll understand why reaching Mars may be far more difficult than most people imagine, why distance and radiation create problems that no single invention can erase, how human biology and economics narrow the path even further, and why the greatest barrier to becoming a multi-planetary species may not be our technology, but the universe itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The confidence surrounding Mars is no longer confined to science fiction. Elon Musk has spoken of building a city of 1 million people there. NASA is preparing for eventual crewed missions. Governments are funding the technologies that might carry humans across interplanetary space. What once belonged to distant speculation now appears in official plans, launch schedules, and serious conversations about the future of our species. And the ambition behind that vision is magnificent. We are the species that looked at the ocean and built boats, that looked at the sky and built planes, that now looks at Mars and builds rockets. This instinct runs deep. It was inherited from ancestors who left Africa, crossed ice bridges, sailed into open water, and populated every corner of a planet that had no obligation to welcome them. That drive is real. It is one of the finest things about us. But every journey in that history took place on Earth. However distant or hostile the destination, the travelers remained inside the same biosphere. They still had breathable air, familiar gravity, accessible water, and some possibility of rescue. Mars offers none of those things. Before considering what happens after humans arrive, there is a more immediate problem: reaching it in the first place. Mars is, on average, roughly 225 million kilometers from Earth. But even that number is misleading, because Mars is not a fixed destination. Earth and Mars orbit the Sun at different speeds, constantly changing the distance between them. At their closest, when both planets are positioned on the same side of the Sun, the gap can shrink to around 55 million kilometers. At their farthest, when they lie on opposite sides, it can exceed 400 million kilometers. That is more than 7 times the distance between the same two worlds, depending entirely on when the journey begins. This matters because you cannot fly to Mars whenever you want. The geometry has to cooperate. Launch windows open only every 26 months, when the alignment is close enough to make the journey practical. Miss the window and you wait more than 2 years for the next one. That constraint alone reshapes every planning timeline. A mission delayed is not a mission postponed. It is a mission held hostage by orbital mechanics. Now consider speed. The fastest spacecraft ever launched past Mars was NASA's New Horizons probe, which passed Mars at around 58,000 kilometers per hour on its way to Pluto. That is extraordinarily fast. At that speed, crossing the 55 million kilometer gap at closest approach, the trip would still take more than 30 days. But here is where it gets strange. We cannot send humans at anything close to that speed. Not because we lack ambition, because of mass. A crewed mission to Mars is not a small probe. It is a vessel carrying human beings, which means it carries massive fuel reserves, food and water for months, life support systems, medical equipment, radiation shielding, and the supplies needed for the surface mission and the journey home. All of that mass requires far more propulsion to move, and far more fuel to carry that propulsion, which adds more mass, which requires more fuel still. The faster you want to go, the worse this problem gets. The mathematics of moving large masses through deep space does not scale gently. It compounds. The result, under current NASA planning, is a transit time of roughly 9 months each way. Not 30 days. 9 months. Think about what 9 months means. 9 months trapped inside a metal container smaller than a studio apartment. No gravity to hold bones and muscles together. No meaningful exercise that fully compensates for what weightlessness does to the body. And above all, radiation. Deep space is flooded with cosmic rays and solar particle events. The kind of high-energy radiation that Earth's magnetic field and thick atmosphere quietly absorb on our behalf every single day. In deep space, that protection is gone. The walls of a spacecraft offer some shielding. Not enough. The comparison that clarifies this is the Moon. The Apollo missions took roughly 3 days to reach lunar orbit. 3 days of exposure, 3 days of confinement, 3 days of risk, then return. The crews came back weakened, but intact. 9 months is not a longer version of that journey. It is a categorically different kind of challenge. The body does not just experience more of what it experienced during Apollo. It experiences something Apollo never touched. Bone density loss that compounds month after month. Muscle atrophy that rehabilitation can only partially reverse. Radiation accumulation that raises lifetime cancer risk with every passing week. Immune system changes that researchers are still working to fully understand. That is the journey. Before Mars is even reached. Before the landing. Before any question of shelter, food, water, or return. The trip alone already begins to break the body that needs to function on the surface. And that is only the first problem. The distance is not what kills you. It is only what gives the real killer time to work. Earth wraps every person on its surface in 2 layers of protection so complete, so constant, that most people never think about them. The first is the magnetic field, a vast invisible bubble generated by the churning iron in Earth's core. It deflects the charged particles streaming out from the sun and the cosmic rays hammering in from deep space, bending them away before they reach the surface. The second is the atmosphere, a thick column of air above every square meter of ground, absorbing what the magnetic field misses. Together, they filter out radiation levels that would otherwise make the surface unlivable. We do not experience this protection because it is invisible, and we have never lived without it. The moment a spacecraft leaves that bubble, both layers disappear. What replaces them is nothing. A thin metal hull and space. The radiation levels a crew would face during transit to Mars are not elevated compared to living on Earth. They are not in the range of concern. They are in the range that would be illegal exposure for nuclear power plant workers, people whose entire profession involves careful management of radiation risk. That is the baseline. That is the opening condition before Mars is even in view. NASA's Curiosity rover gave us a direct measurement. During its cruise to Mars, Curiosity carried a radiation detector, and the data it sent back was precise. The round-trip transit dose for a human crew making the same journey would be approximately 660 millisieverts. And the transit is only part of the exposure. Mars offers no protection. Earth's magnetic field deflects the worst of the incoming radiation before it ever reaches the atmosphere. Mars lost its global magnetic field billions of years ago. Its atmosphere is approximately 1% as thick as Earth's, a thin veil that provides almost no shielding against cosmic rays or solar particle events. Standing on the Martian surface, you would receive roughly 230 microsieverts of radiation per day. That is the equivalent of a chest X-ray every 3 days, sustained indefinitely. Over a 2-year surface mission, the accumulation would significantly raise the risk of cancer, cataracts, and sterility. DNA strands would be under constant assault. But something was wrong. Cancer risk, as serious as it is actually the less alarming part of what radiation does to a human body in deep space. For a long time, the primary concern was the cancer question: elevated lifetime risk, probabilistic harm, a statistic distributed across decades. That framing made the problem sound manageable, the kind of elevated risk that could be weighed against the mission's importance and accepted. Then, researchers started looking more carefully at what cosmic radiation does not to the body in general, but to the brain specifically. The particles are not like the photons in an X-ray. Cosmic rays include heavy, high-energy atomic nuclei traveling at a significant fraction of the speed of light. When one passes through biological tissue, it does not diffuse or scatter gradually. It punches a path through cell membranes, through proteins, through neurons, through DNA. The damage is localized and direct. Studies on mice exposed to cosmic radiation levels comparable to what a Mars crew would face showed significant brain damage and measurable behavioral changes. The mice developed problems with memory, cognition, and motor function. These are animal models, not human clinical trials, and that distinction matters. What happens in a mouse brain cannot be translated directly to a human brain. But the biological mechanisms being disrupted, the same mechanisms that govern memory formation and cellular integrity in human neurons, do not belong to mice alone. The damage works through multiple pathways. One of them begins at the DNA level and ends somewhere far more unsettling. Cosmic rays do not simply break DNA strands. They trigger cascading reactions that produce free radicals, unstable molecules that tear through the cellular environment, destroying proteins, lipids, and the membranes that hold cells intact. The brain is particularly vulnerable to this kind of damage because neurons are largely post-mitotic cells. Most of them do not divide and replace themselves the way other cells in the body do. When a neuron is lost or damaged, it is often gone. When its synaptic connections, the links that form memory and cognition, are destroyed. Rebuilding them is slow, incomplete, and sometimes impossible. The research shows that cosmic radiation causes brain inflammation. It destroys synapses. It triggers protein misfolding of a kind that resembles the pathology seen in Alzheimer's disease. Not a statistical elevation of risk. A structural process, unfolding in real time, producing the same kind of neurological damage that eventually turns a functioning person into someone who no longer recognizes their own name. After several years on Mars, colonists would not merely face elevated cancer risk. They would likely face cognitive decline, memory loss, confusion, and personality changes. Gradually, irreversibly. The phrase the research suggests, put plainly, is a colony of people slowly losing their minds. And radiation may not be working alone. Research on astronauts aboard the International Space Station shows that spaceflight causes premature aging at the cellular level. Telomeres, the protective caps on the ends of chromosomes that maintain the stability of DNA during cell division, behave strangely in space. They lengthen during flight, then shorten rapidly upon return, a pattern associated with accelerated aging and elevated cancer risk. DNA damage accumulates faster than it does on Earth. The combination of sustained radiation, microgravity, and physiological stress creates a compounding effect. How much faster colonists would age is not precisely established. Some estimates suggest the pace could be 2 to 3 times that of normal aging on Earth. That figure comes from the source material and is not independently attributed here. But even if the real number is smaller, the direction is not in question. Every biological clock runs faster. The instinctive response to all of this is to ask about shielding. If radiation is the problem, build a better wall. Line the spacecraft with lead. Fill the hull with water. There is real research into radiation shielding, and some materials do better than others. But cosmic rays are not like ionizing radiation from a nuclear source, which can be blocked with relatively modest thicknesses of dense material. High-energy cosmic ray particles require mass, significant mass. Stopping them would require meters of lead or meters of water surrounding the crew compartment. Not centimeters, meters. A spacecraft capable of carrying that mass would itself require vastly more fuel, which requires more mass, which requires more fuel still. The rocket equation does not bend to optimism. Every kilogram of shielding added to the structure compounds the problem of getting the structure off the ground and across space. There is no engineering shortcut waiting to be discovered. There is no material that stops cosmic rays cheaply. Radiation is not an engineering problem with a solution currently under development. It is a barrier, possibly a permanent one, and radiation is not even the whole of what a body faces once it arrives. Suppose we solved it. Suppose some future technology answered the radiation problem completely. Suppose the cosmic rays were stopped, the solar particle events blocked, the neurological damage prevented. Suppose all of that. The body still comes apart, not from what Mars sends at it, but from what Mars fails to give it. Mars has gravity. That matters. It is not the weightlessness of orbital spaceflight, where bones dissolve faster and muscles vanish in weeks. Mars pulls at you, but it pulls at about 38% of what Earth's gravity does. That is just over a third. And your body did not evolve for a third. It evolved for the full pull of Earth over hundreds of millions of years, and every system inside it, bone, muscle, cardiovascular, immune, depends on that pull being present and constant. The numbers from orbit give us the clearest warning we have. On the International Space Station, astronauts lose roughly 1% of their bone mass per month. Not over a career, per month. Even with rigorous daily exercise regimens designed specifically to slow the loss. Even with the best countermeasures available, they still return after 6 months noticeably diminished, requiring months of rehabilitation. Mars gravity would slow that rate. It would not stop it. The pull is real, but it is not enough. After a year on Mars, after 2 years, after 5, the loss accumulates. And here is where the problem deepens past what most people expect. It is not just density. That is the first assumption, and it is wrong. Bones do not simply become less dense on low gravity, they remodel. The interior architecture changes. Trabecular bone, the spongy inner structure that gives bone its load-bearing strength, the scaffolding inside your femur and your vertebrae and your hip socket, deteriorates preferentially. Weight-bearing joints degrade. The geometry shifts. And studies on astronauts who have returned to Earth show that this remodeling does not fully reverse. Not in months. Not in years. The structure that changed appears, in many cases, to stay changed. Colonists on Mars would not simply be weaker than when they left. They would be permanently altered by Earth standards. Permanently disabled. A body shaped by Mars, incompatible with the planet it came from. Think about what that means for the question of returning home. The heart adapts to reduced gravitational demand. It does not need to push blood as far or as hard in a lower gravity environment, and over time it does less. Blood volume decreases. The cardiovascular system recalibrates for a world that asks less of it. Then, imagine that person stepping onto an Earth launch pad after years on Mars. The heart, recalibrated for 38% gravity, now has to push blood upward against a full G. The bones, remodeled for Martian loads, now have to bear full Earth weight. Walking could fracture them. Not the fractures of old age, fractures from walking. The people we send to Mars would not just be unlikely to come home, many of them would be physically incapable of surviving the attempt. The picture did not hold. The gravity effects we expected, bone loss and muscle atrophy, turned out to be only part of the picture. Recent studies on astronauts returning from the ISS revealed changes no one had put on the list of concerns. The shape of the eye changes in microgravity. The eyeball itself deforms slightly, and that deformation causes vision problems. Those problems do not fully reverse on return to Earth. Brain scans on returning astronauts show structural changes, cerebrospinal fluid accumulating in ways that alter the brain's internal environment, changes that may carry permanent cognitive effects. Some astronauts develop blood clots in the jugular vein, not a known risk before, not something that appeared in the pre-mission models. A potentially fatal condition discovered after the fact, in people who had already experienced it. The human body may not just be poorly suited to long-duration spaceflight, it may be fundamentally incompatible with it, and the immune system does not emerge from this intact. ISS research over decades has documented consistent immune suppression in astronauts. White blood cell counts drop. Antibody production decreases. Dormant viruses, herpes strains that have been latent in the body for years, reactivate. All of this within 6 months, in low orbit, with partial protection still provided by Earth's magnetic field. On Mars, with higher surface radiation and no protective field, with permanent exposure and no reprieve, the immune suppression would be deeper and sustained indefinitely. A cold spreads through a healthy, vaccinated population, and most people recover. A cold spreads through a population with a severely compromised immune system, And people die. The source of infection barely matters. The body's ability to fight it does. There is one more vulnerability that gets less attention than it deserves. Humans are not individuals in the biological sense. We are ecosystems. Each person carries trillions of microorganisms, bacteria and fungi and viruses that live in and on the body, helping digest food, produce vitamins, regulate immune responses, and influence neurological function. This community, the microbiome, is not a passenger. It is infrastructure. Remove it and digestion fails. Immunity collapses. Mental health destabilizes. On Mars, radiation would damage microbial populations alongside human cells. Different gravity would alter the gut environment those organisms depend on. Colonists would be cut off from Earth's vast reservoir of microbial diversity, the constant ambient exchange that refreshes and replenishes our internal ecology on Earth. The environment would be sterile, and because the immune system would be weakened, antibiotics would be needed more frequently, which would further destroy the beneficial bacteria that remain. Within years, colonists could suffer malnutrition not from a lack of food, but because the microbiome needed to process that food no longer exists in functional form. They could suffer immune disorders, digestive failures, neurological deterioration, all from a collapse that unfolded silently, below the threshold of visible symptoms, until the damage was done. There is one more question that gravity raises, one that reaches further than the health of the colonists already there. Whether human pregnancy is even possible in reduced gravity is something we do not know. The research simply does not exist. No mammal has been gestated in partial gravity, and the developmental demands of a growing fetus, the formation of bone, the calibration of the vestibular system, the regulation of blood pressure and fluid distribution, all depend on gravitational cues we have never tested at 38%. That question will be taken up later, but it is worth knowing it is waiting. It is also worth being honest about the limits of what we do know. Most of what we understand about long-duration gravity effects comes from the ISS, from microgravity, from 0G, not from 1/3 G. Mars is not the ISS. The deterioration on Mars would likely be slower. But extrapolating from 0 to 38% is not the same as measuring 38% directly. We have never measured it. The curve between those 2 points is real, but its shape is unknown. What we can say with confidence is that 38% does not make the problems disappear. It changes their pace. The destination, for those who stay long enough, appears to be the same. The body the first colonists carry to Mars will not be the body that serves them indefinitely. It will be a body in slow, compounding transformation. And the gravity problem does not arrive alone. The planet outside is not waiting politely. While the body is slowly remodeling itself from within, bone by bone, synapse by synapse, the environment pressing against the habitat walls is working from the other direction. And the first thing it sends through is something that sounds, at first, like a housekeeping problem. Dust. Mars is covered in it. The entire surface is coated in a fine, rust-colored powder that the wind picks up and carries across continents, across hemispheres, eventually across the whole planet. And the word dust makes you picture something you wipe off a shelf. Something manageable. Something that stays where you put it. But here's where it gets strange. Martian dust is not like Earth dust. The particles are approximately 3 micrometers across. That is smaller than a red blood cell. Particles that size do not settle in your sinuses or your throat. They travel straight past the body's first lines of defense and embed themselves deep in lung tissue. And once there, they do not come out. That alone would be a serious problem. But the physical size of the particles is not even the most dangerous thing about them. Martian soil contains perchlorates. These are chemical compounds, chlorine-based salts, that occur naturally across the Martian surface and have been detected at concentrations reported to be roughly 10,000 times higher than levels considered safe for human exposure on Earth. Perchlorates interfere with the thyroid gland. The thyroid regulates hormones that govern metabolism, development, and neurological function. Chronic perchlorate exposure disrupts that regulation. In adults, it degrades hormone production. In children and in developing fetuses, it can cause permanent developmental damage. So the dust is not a nuisance, it is a thyroid-disrupting toxin at concentrations orders of magnitude above anything the human body is designed to tolerate, delivered in particles small enough to bypass every protective mechanism your lungs possess. and NASA has not solved how to keep it out. This is not a matter of better filters or better airlock design still in development. The Spirit and Opportunity rovers were designed for 90-day missions. They survived for years, far exceeding every projection. But they survived partly because Mars occasionally produces wind events strong enough to clean accumulated dust from their solar panels. Lucky gusts at the right time extended their lives. A human colony cannot be managed on lucky gusts. Every time a colonist returns from a surface walk, the suit carries dust back through the airlock. That dust enters the habitat. It settles on surfaces, on equipment, in ventilation systems, and eventually into the air the colonists breathe. Over months and years, it accumulates. Think about what that means. It is not a bad day when the filtration fails. It is a slow, continuous accumulation of a toxic compound in every breath taken inside the habitat, with no mechanism to halt it and no ability to leave. The source material offers an image that stays with you. Living on Mars, it suggests, is like trying to live in a world made of poisonous talcum powder that is also magnetic. The dust clings. It is electrostatically charged, so it adheres to suits, to visors, to equipment surfaces, to anything it touches, and it resists every attempt to brush or clean it away. Now, consider what happens when the wind picks that dust up at scale. Mars dust storms can grow to cover the entire planet. Not a regional weather event. The entire planet simultaneously for months at a time. The dust is so fine that in these conditions it behaves almost like a fluid. It does not merely reduce visibility, it penetrates sealed containers. It works through gaps in equipment seals that would stop larger particles entirely. It coats solar panels until they produce almost no power. It abrades mechanical parts. It carries not just perchlorates, but heavy metals and possibly other compounds whose long-term biological effects are not yet understood. Months of breathing air laced with these substances, in a habitat that cannot be made fully airtight against particles this fine, is a chronic exposure problem with no ceiling and no remedy. But the dust storms carry something else, something that transforms them from a visibility and power problem into something far more dangerous. Wait, global Martian dust storms are electrically charged. The friction of billions of dust particles moving against each other and against the surface generates massive triboelectric charging across the storm system. Not static electricity at the scale of a door handle. Planet-wide electrical phenomena lasting months. These electrical fields can destroy unshielded electronics. They can disrupt communication systems. They can damage or eliminate solar power generation entirely. And static discharge from a charged dust environment could injure an astronaut inside a suit, or cause catastrophic ignition in a facility producing fuel from atmospheric gases, which is how any Mars colony would need to generate its rocket propellant for the return trip. We have no technology to protect a surface installation against a planet-wide electrical storm lasting months. None exists. One major storm event arriving at the wrong moment could eliminate a colony's power generation, its communications, and its electronics in sequence. The colonists would be left without the tools to repair any of it. Set that aside for a moment, and step outside the storm. The thin atmosphere that enables the dust to behave this way is itself a separate, constant danger. Mars' atmospheric pressure is less than 1% of Earth's. Without a pressure suit, the dissolved gases in your blood would nucleate and expand. Your blood would boil, not metaphorically, literally, in under a minute. This means every single surface excursion, every repair job, every sample collection, every check on the exterior of the habitat requires a full pressure suit, not an oxygen mask, as in certain films where characters step outside briefly without one. A complete pressure containment system. These are complex machines. They have seals that degrade, joints that wear, helmets that can crack. One small tear, one faulty seal at a wrist joint or a boot ring, and the person wearing it dies in under a minute. There is no time to patch it and no medical intervention that addresses the immediate pressure loss. And even inside a functioning suit, the temperature the planet produces makes everything harder to maintain. Near the equator in summer, Martian noon can reach approximately 20 degrees Celsius, briefly comfortable, but Martian nights at the same location drop to approximately negative 73 degrees Celsius. That is a swing of nearly 100 degrees between noon and midnight, every single sol, every Martian day, without exception. At the poles in winter, temperatures fall to around negative 125 degrees Celsius. cold enough for carbon dioxide to freeze directly out of the atmosphere and fall as dry ice snow. That daily temperature swing does not merely require good insulation. It imposes a mechanical stress cycle on every material used in construction. Metals expand and contract, seals compress and relax, joints flex and stiffen. Repeat this hundreds of times, and the cumulative fatigue begins to compromise structural integrity. Add abrasive dust, working into every seam during every cycle, and the degradation accelerates further. The result is a maintenance burden unlike anything humans have managed in isolated conditions on Earth. Seals fail from thermal cycling, metal fatigues from repeated expansion and contraction. Electronics degrade from radiation. Solar panels lose efficiency from dust accumulation. Mechanical components wear from constant abrasion. On Earth, maintaining complex infrastructure is a profession. Entire industries exist to service, repair, and replace the systems that keep facilities running. On Mars, a small crew must absorb all of that themselves, on top of their primary mission objectives, with no supply chain and a waiting time for replacement parts measured in years. The arithmetic is brutal. A crew spending most of its waking hours on maintenance is not doing science. It is not building expansion modules. It is not preparing the infrastructure for the next arrival. It is running in place, trying to keep the environment from reclaiming what was built. And maintenance is only possible as long as you have the parts to do it. That problem runs deeper than a supply shortage. It reaches into something structural about what a Mars colony would actually need to become self-sufficient. But the environment demanding those repairs, demanding that constant labor, demanding that the colony produce everything it needs from the resources immediately available, is itself only partly described by a dust and temperature and thin air. The biggest constraints on what a Mars colony can build and sustain are still ahead. Of all the systems slowly wearing down out there, 2 cannot be allowed to fail even once. Not degrade gracefully, not lose efficiency over time. Fail completely once, and the colony ends. Those 2 systems are food and water. And neither has ever worked perfectly, even with the full weight of Earth behind them. Start with the ground itself. The obvious solution for growing food on Mars is to use Martian soil. Mars has soil. Plants need soil. The logic seems straightforward. But Martian soil is not like Earth soil in any way that matters for growing food. It is laced with perchlorates, the same chlorine-based compounds covered earlier, at concentrations that would poison most plants long before they could fruit. It is missing the nutrients Earth crops depend on. And it is missing something else, something harder to replace than nutrients. Soil on Earth is alive. A single teaspoon of healthy farmland contains thousands of species of bacteria, fungi, nematodes, and other microorganisms. Those organisms break down organic matter, fix nitrogen, regulate chemistry, and create the conditions that allow roots to establish and plants to grow. Martian soil has none of them. It is chemically hostile and biologically empty. Growing food in it would be more like growing food in a mixture of sand and bleach than in anything resembling farmland. Antarctica, at its coldest and most barren, still has surface microbial communities. Mars does not. Growing food on Mars makes Antarctica look like paradise. You might have seen a different picture in the film The Martian, where an astronaut grows potatoes in Martian soil by mixing it with human waste. It is a compelling image. It is also wrong. Those potatoes would not grow, not stunted, not reduced in yield. They would be poisoned by perchlorates before they established, and even if the chemistry was somehow corrected, the biological infrastructure to support plant growth simply would not be there. Soil is not a substrate, it is an ecosystem, and that ecosystem took hundreds of millions of years to build on Earth. Recreating it on Mars from scratch, with a small crew and no supply of Earth organisms, may not be possible. Hydroponics seem like the answer. Skip the soil entirely, grow plants in nutrient solutions, control everything artificially. And hydroponics would certainly be part of any serious Mars agricultural plan. But hydroponic systems are not simple. They require precisely balanced nutrient concentrations, constant monitoring of pH and mineral levels, pumps, filtration systems, and regular replacement of degrading components. Every one of those components is a point of failure. On Earth, a hydroponic farm that loses a pump loses a crop. It orders a replacement, absorbs the loss, and continues. On Mars, losing a pump could mean losing the colony's food supply entirely. There are no backup suppliers. There is no import mechanism. There is the equipment that was brought, and when it fails, There is waiting 2 years for the next launch window, if a replacement was even packed. The psychological pressure on whoever manages food production under those conditions would be extraordinary. One mistake, one overlooked contamination, one component wearing past its tolerance, and everyone starves. The atmosphere creates its own contradiction. The Martian atmosphere is 95% carbon dioxide, which sounds at first like good news for plant growth. Carbon dioxide is what plants breathe. More of it should mean faster growth. But the Martian atmosphere is also toxic to humans at those concentrations, so you could not simply grow crops in the open air. You would need pressurized greenhouses with controlled atmospheres, sealed against the outside, heated through the frigid nights, and artificially lit to compensate for a sun that delivers only 43% of the energy it delivers on Earth. Most Earth plants simply cannot photosynthesize enough under that light level to sustain meaningful growth. The power requirements for heating, lighting, and pressurizing those greenhouses would be enormous, pulling from the same constrained power budget that every other colony system depends on. And then there is time. Mars has a day that runs 24 hours and 37 minutes, just slightly longer than Earth's. That small difference would gradually desynchronize the circadian rhythms of both colonists and their plants. Earth crops evolved across millions of years for specific day lengths, seasonal light cycles, and spectral compositions of sunlight. The light spectrum on Mars differs from Earth's in ways that affect how plants trigger flowering and fruiting. Many food crops will not produce food without the right environmental cues. Without Earth's seasonal shifts, without the pollinators that trigger reproduction, without the atmospheric pressure and day-length cycles plants evolved to respond to, even well-established crops would struggle to produce anything edible. Genetic modification could potentially address some of this, but that kind of biotechnology requires industrial infrastructure a small colony cannot support. Something else was happening. The thing that sounds most like a solution, water, turns out to be almost as complicated as the soil. There is water on Mars, ice at the poles, and probably frozen underground in various locations. That water sounds like a lifeline. For years, the discovery of dark seasonal streaks on Martian slopes, called recurring slope lineae, generated tremendous excitement. Flowing water on Mars. The kind of water that could mean something for a colony. The reality is grimmer. Those streaks are likely caused by dry granular flows, or, at most, tiny amounts of brine. If it is water near saturation with dissolved salts, sitting at around -50 degrees Celsius and laced with perchlorates. Imagine drinking from the Dead Sea, except the water is also at -50 degrees Celsius and contains perchlorates. That is not the life-giving water of science fiction. It is a toxic chemical soup, hostile to all known life. Extracting water from the more promising sources, the polar ice caps and underground frozen deposits, requires digging through frozen regolith that is harder than concrete, then melting the ice, then purifying water that is almost certainly contaminated with the same perchlorates and heavy minerals that contaminate everything else on Mars. The energy cost of that process, at scale, is staggering. And unlike Earth, where the water cycle continuously purifies and redistributes fresh water through evaporation, rain, and flow, on Mars every molecule of water must be managed artificially, every step of the way. That management requirement brings us to the loop. On the ISS, water is recycled from urine, sweat, and humidity in the air. The system is sophisticated. It achieves roughly 93% recovery, not 50%, not 70%. 93% of the water that enters the system comes back out as usable water. That is a remarkable engineering achievement. It is not enough. The ISS still requires regular resupply. That remaining 7%, the water that leaks from seals, escapes in exhaled breath, gets trapped in waste that must be disposed of, cannot be recovered. On Earth, that gap is closed by a resupply flight. On Mars, there are no resupply flights, except once every 26 months, and they carry equipment, not water. A Mars colony would need to close that loop almost entirely, not 93%, something approaching 99 or 100% sustained for years, across all systems, without replacement parts. The ISS has every resource of human civilization available to it. Hundreds of engineers on the ground monitoring its systems in real time, parts that can be launched within months. Astronauts cycling home every 6 months before cumulative damage becomes permanent. And still the ISS cannot close its loop. Still it loses water. Still, it requires constant replenishment of air. Still, it produces waste it cannot fully process. The ISS is a marvel of engineering, and it cannot do what a Mars colony would need to do from day one. On Mars, every seal that leaks is water loss permanently. Every filter that clogs is contamination spreading through the system. Every pump that fails is a step toward a colony that is slowly dehydrating, slowly starving, slowly suffocating as the loops it depends on lose efficiency, one component at a time. The degradation would not be sudden. It would be gradual, cumulative, quiet. A colony not dying in a single disaster, but fading as the machinery that keeps it alive slowly falls behind the minimum threshold. Whether Earth's living soil ecosystem could ever be recreated on Mars remains genuinely open. No one has done it. No one yet knows how. But the closed-loop question has already been answered, in the only real-world test that exists. The ISS ran the experiment, with everything Earth could give it, and the loop did not close. What food and water demand from a Mars colony is not a version of what the ISS does. It is something no one has ever built, running without support in a place that will not forgive the first serious failure. And that is only the foundation. What a colony must build on top of those loops is still to come. Suppose the machines hold. Suppose the water loops close and the greenhouses grow and the pressure suits seal perfectly every time. There is still someone inside all of that machinery. Someone who said goodbye to everyone they loved, knowing the word goodbye meant something permanent. And they are 28 light minutes from any voice that can answer them back. That is not a metaphor. The average distance between Earth and Mars means that any signal traveling at the speed of light takes roughly 14 minutes to arrive. You send a message. You wait. The earliest possible response comes back 28 minutes later. Not a slight communication lag. Not a bad connection. The conversation structure that every human being has relied on since birth, the back and forth rhythm of someone hearing you and answering, is gone. There is no real-time anything. No live conversation with a spouse or a child. No voice on the other end of a crisis. No one to call when something goes wrong and the answer is needed in the next 5 minutes. You are more isolated than any human being has ever been. More isolated than anyone in Antarctica, anyone on a submarine, anyone at the edge of the world. They could always at some point reach someone who could respond. On Mars, you cannot. What that does to a mind over months and years is not theoretical. We have data. In 2010, a research team ran an experiment called Mars 500. 6 volunteers agreed to be sealed inside a simulated Mars habitat for 520 days, roughly the length of a full Mars mission. They knew they could leave. Home was a door away. They had full communication with the outside world. No radiation, no perchlorate dust, no life support loops counting down. Just confinement, a small group, and time. The psychological stress was severe. Crew members developed depression. Sleep disorders spread through the group. Conflicts grew and did not resolve. And one crew member, somewhere in the long middle of the experiment, simply stopped. He retreated to his bunk. He stopped engaging with the mission, with the group, with the simulation. He stayed there for days. That was with an unlocked door. That was with Earth gravity and Earth air, and the ability to call home in real time. That was a simulation. The experiment was designed specifically to test psychological resilience in carefully selected, highly motivated volunteers. On actual Mars, every single one of those mitigations disappears. A mental breakdown does not get sent home. A crew member who retreats to their bunk stays there. Irreconcilable conflicts between people who must work together to survive do not get resolved by distance or time apart. The group is locked. The situation is permanent. And the source of pressure does not ease. The source material does not soften what that arithmetic leads to. Murder-suicides, psychotic breaks, and complete social breakdown are not distant worst cases. They are probable outcomes, given what we know about human psychology under sustained extreme confinement. That is a blunt conclusion, but it follows from blunt evidence. Part of what makes it blunt is the sensory environment. The psychological challenge sounds, from a distance, like homesickness and boredom. It is not. Homesickness and boredom are features of a human environment that is simply inconvenient. What Mars offers is something different. It is sensory deprivation on a planetary scale. Think about what every comfort cue in your nervous system was built for. Rain. The smell of soil after rain, the sound of wind in leaves, animals moving, the sky changing colour, seasons shifting, the chaos and variety of a living world. Every one of those cues is the product of billions of years of evolution shaping a nervous system to respond to a living environment. None of them exist on Mars. Not muted, not reduced, absent. There is no rain on Mars. No snow except carbon dioxide snow at the poles in winter. No clouds worth speaking of. Just thin wisps that carry no weather and cast no shadow. No animals, no plants, no soil smell. The sky is not blue. It is butterscotch during the day and green at sunset. The optical result of suspended dust particles scattering light in a spectrum opposite to Earth's. The sun is noticeably smaller and dimmer. The familiar star patterns at night are shifted because you are seeing them from a different point in the solar system. The ground is red. The rocks are red. The horizon is red. Every day. Forever. That is not boredom. That is the total removal of every environmental signal the human brain evolved to find meaningful. We already have evidence of what a fraction of that removal does on Earth. Seasonal affective disorder, the depression that accompanies reduced winter sunlight, affects tens of millions of people every year from nothing more than shorter days and less direct sun. Research consistently shows that reduced exposure to natural environments increases depression, anxiety, and measurable cognitive decline. On Mars, the sun is dimmer year-round, the sky is never blue, there is no nature of any kind, and the confinement is complete. Add isolation, the constant background awareness of danger, and the knowledge that return is not coming. And you have conditions under which widespread psychological breakdown is not a risk to be managed. It is a likely outcome to be planned around. The social layer compounds everything. A Mars colony would be a small group. The same faces, every meal, every shift, every conflict. On Earth, personality clashes resolve through distance. You change jobs, you move, you find new people, you create physical space between yourself and someone you cannot get along with. On Mars, there is no space to create. Every interpersonal tension becomes a survival question, because the person you cannot stand is the person who fixes the water recycler and operates the emergency decompression valve. The social dynamics of isolated groups are well documented. Polar expeditions, remote military postings, submarine crews, all of them composed of trained, vetted, motivated people. All of them producing severe conflicts, psychological deterioration, and in some cases outright violence. Those situations lasted months. A Mars colony lasts lifetimes. The powder keg is not a metaphor. It is a description of a social structure with no pressure release. And then there is time itself. A Mars day is 24 hours and 37 minutes, not dramatically different from Earth's. Close enough that it almost does not seem worth noting. But small differences, compounded daily, accumulate. After a month, Mars and Earth schedules are offset by a full day. After a year, coordination with Earth requires constant recalculation. The colonists would not just be physically separated from Earth civilization. They would gradually be living in a different time. Their days drifting out of alignment with every schedule and rhythm Earth operates on. That drift is not merely administrative, it is a slow deepening of the sense of separation, a daily reminder that the world they came from is no longer synchronized with the world they inhabit. We do not fully understand how that combination of isolation, sensory deprivation, social entrapment, and temporal drift would compound over years and decades. The Mars 500 experiment gives us a partial answer, and even that partial answer is not reassuring. What it suggests is that the psychological architecture required for a Mars colony is something no training program has yet produced, and no simulation has yet tested at full fidelity. The engineering problems have engineering answers, even when those answers are incomplete. The psychological problem has a different shape, and the machinery of the mind is the one system in the entire colony with no redundancy at all. There is no sending anyone home. That sentence is bleakest not in the abstract, but in the body. On the day something in it goes wrong. On Earth, a heart attack means someone calls an ambulance. A stroke means a hospital within the hour. A traumatic injury from a fall, a tool slip, a suit malfunction means emergency care arrives before the window closes. The distance between the injury and the treatment is measured in minutes. On Mars, the nearest hospital is 9 months away. And that is only true if the planets are in the right alignment to launch at all. If the launch window has passed, The wait is not 9 months. It is 9 months, plus however many months remain until the next window opens. A broken bone that on Earth would mean a cast, and 6 weeks of recovery could, under the wrong circumstances, mean infection, immobility, and death. Appendicitis, kidney stones, a dental abscess that spreads to the jaw and then deeper. These are not exotic emergencies. They happen to ordinary people on ordinary days. On Mars, they become problems that the available equipment and the available expertise may simply not be able to solve. Here is the expertise problem. The first Mars missions will have perhaps 4 to 6 people. That is the whole crew. That is everyone. You cannot bring a cardiologist, a neurosurgeon, an oncologist, an obstetrician, an anesthesiologist, and a trauma surgeon. You bring whoever you bring, and you hope the emergencies stay within their training. The crew doctor might be excellent, trained in emergency medicine, capable in surgery, experienced in wilderness medicine or aerospace medicine. But wilderness medicine has a ceiling. When a colonist develops a brain bleed, or a cancer that needs imaging and chemotherapy, or goes into premature labor, the ceiling arrives. There is no one else to call. There is no specialist on the next floor, and the gap between what is needed and what is available is not a gap that skill or preparation can close. It is a gap in numbers. But the reality was different. Even if you had a surgeon, operating on Mars is not the same as operating on Earth. Blood does not pool the way surgeons are trained to expect. Fluids behave differently in reduced gravity. The physical mechanics of an open body procedure, built on decades of training in Earth gravity, change in ways that are not obvious until you are already inside the patient. A surgeon who has spent a career operating in one gravitational environment would be working, on Mars, in a subtly alien version of the same room. The instruments are familiar. The anatomy is familiar. The physics is not. And then there is the medicine cabinet. Medications have shelf lives. Most were designed to be stored under controlled conditions and used within a defined window. Some degrade quickly even under ideal conditions. High radiation environments accelerate that degradation. An ISS study found that medications lose potency much faster in space than they do on Earth, faster than the labeled expiration dates predict. A Mars mission carries medical supplies chosen years before departure, launched months before arrival, then stored on the surface in conditions that actively shorten their effective life. The crew does not run out of medicine in the dramatic sense. The medicine is there. The bottles are full. But the compounds inside have been quietly breaking down since before the mission launched. A drug that is supposed to control seizures, manage infection, or stabilize cardiac rhythm may be delivering a fraction of its intended dose. You cannot order a replacement. There is no Martian pharmacy. Every molecule of every medication that will ever exist in that colony was either packed in a cargo hold before departure, or will not exist at all. Not reduced, not slightly less effective, potentially useless. At the moment, it is most needed. And here is the part of the medical conversation that almost no one wants to have. People will die on Mars, not as a risk, not as a possibility that careful engineering might prevent, as a certainty, from accidents, from medical events that exceed the available care, from system failures that happen too fast to contain, from suicide, which Antarctic studies and submarine deployments and every other long-duration isolation program confirm is a real and recurring endpoint. People will die. What do you do with the bodies? On Earth? The answer is so obvious we never think about it. On Mars, every option fails. You cannot bury a body in the Martian soil. The soil is laced with perchlorates. It is toxic and chemically hostile, and introducing biological material into it creates a contamination problem the colony cannot manage. Cremation requires energy, an enormous amount of energy, and energy on Mars is a survival resource. Burning a body is burning power that the water recycler and the greenhouse lights and the pressure suits depend on. Storing a body inside the habitat is a health hazard and a psychological burden that compounds every day it continues. The body is still there. Everyone knows it. There is nowhere to take it. Composting has been proposed. Human remains processed into soil amendment for the greenhouse. The logic is resource efficiency. The reality is pathogen risk, biological complexity, and a psychological weight that the Mars 500 experiment gives us no framework for measuring. 6 people, sealed in a habitat, composting their colleague. The discussion exists in technical literature. It rarely makes it into the public conversation about what Mars colonization looks like. The first funeral on Mars will shatter something. Not just morale, the idea. The bright, expansive idea that Mars is where humanity goes to become more than it was. A body with nowhere to go, in a habitat with no ceremony large enough for what happened, under a butterscotch sky, 9 months from anyone who might come. That moment will be real, and no mission architecture document fully addresses it. The medical problem on Mars is not one problem, it is a chain. Evacuation is impossible. The crew is too small to carry every specialty. Even the surgeons they do have will be operating in gravity that does not match their training. The drug supply is degrading, and when the chain reaches its end, there is no acceptable answer for what comes after. The bodies are not the final difficulty. They are the most visible one. Set aside, for a moment, what Mars would do to us. Consider what we have already done to Mars. The conversation about planetary protection almost always runs in one direction. We sterilize rovers, we bake landers in heat chambers, we track contamination levels on every piece of hardware that leaves Earth. The stated goal is to keep Earth microbes off Mars, so that if we ever find life there, we can be certain it is genuinely Martian. That goal is reasonable. It is also, at this point, very likely already compromised. Every Mars rover and lander ever sent has carried Earth microbes with it. Some bacteria and fungi survive the sterilization process. Some survive the journey through deep space. A small number of species are hardy enough that Mars conditions, brutal as they are, may not kill them. We know this. We have known it for decades. The implication follows quietly and lands hard. If we find life on Mars, we may not be able to prove it is Martian. It might be ours. A contamination passenger from a 1970s lander, a hitchhiker on a rover wheel, a microorganism that survived sterilization, survived transit, and found some marginal niche in Martian regolith. We would have no way to distinguish it from indigenous Martian life with absolute certainty. The scientific rationale for going to Mars, in large part, is to answer the question of whether life exists, or has existed there. That question may already be contaminated beyond a clean answer. That is when the pattern broke. Because the contamination problem does not only run from Earth to Mars, it runs the other way too, and that direction is the one nobody discusses honestly. Mars may harbor life we do not know about. The probability is uncertain. The consequences of being wrong are not. If a returning astronaut carries a Martian microorganism back to Earth, and if that organism can survive in Earth's biosphere, no existing quarantine system can guarantee containment with absolute certainty. After the Apollo missions, NASA quarantined the astronauts for 3 weeks. The Moon was considered sterile. Mars is not considered sterile. Mars quarantine for returning astronauts would need to be far more stringent, far longer, and far more certain than anything we applied to the Apollo crews. And we would need to maintain that certainty not for 3 weeks, but potentially indefinitely, because we would not know what we were looking for. Consider what this means for the sample return mission. NASA and the European Space Agency are spending billions of dollars on a mission designed to bring back a few tubes of Martian soil. That mission will not complete until the 2030s at the earliest. Billions of dollars, years of development, an elaborate return capsule and Earth-based containment facility. For a kilogram of rocks, now scale that to a human being. A human is not a sealed sample tube. A human breathes. A human sweats. A human carries trillions of microorganisms on and inside their body. A human requires food, water, medical care, and social interaction. Containing a human being returning from Mars in the way we would need to contain potential Martian biology is not a logistics problem. It is a different category of problem entirely. The sample return mission is the scale model. If returning a kilogram of rocks requires this level of complexity and this much time and money, the returning colonist problem is not a harder version of the same challenge. It is something we have not seriously grappled with yet. And then there is the insolubility of contamination in practice. Inside the colony itself, every time a colonist puts on a pressure suit and steps outside, they carry Earth microbes with them onto the Martian surface. Every time they come back in through the airlock, they carry Mars dust, and whatever is in that dust, back into the habitat. The suits themselves become contaminated on both surfaces, inside and outside, simultaneously. There is no airlock protocol that eliminates this transfer entirely. There is no decontamination system capable of perfect sterilization in both directions during every single entry and exit over years of habitation. In practice, the colonists will contaminate Mars. Mars will contaminate the colonists. The biological boundary between the two will dissolve slowly and irreversibly. Not because anyone was careless, because perfect biological isolation is incompatible with doing the physical work of staying alive. The Curiosity rover's methane detections illustrate how much we do not understand about what we are proposing to inhabit. Curiosity has detected seasonal releases of methane in the Martian atmosphere. Methane on Mars is scientifically significant because methane breaks down relatively quickly in the Martian environment. Something is producing it. That something is either geological or biological. We do not know which. If it is biological, we have an ethical obligation not to contaminate the organism producing it before we even understand what it is. If it is geological, it represents an unknown chemical process occurring beneath the Martian surface. One that could be reactive, could be dangerous, and could interact in ways we have not characterized with colonists living and working on that surface for years. Either way, we do not understand the planet we are proposing to inhabit. Not fully. Not well enough. The methane question will not be resolved quickly. It may not be resolved before the first crewed missions arrive. That is not a criticism of the science. The universe does not time its answers to our schedules. It is simply the reality. We would be sending people to live on a planet whose chemistry we do not fully understand, whose biological status we cannot confirm, and whose capacity to contaminate us in ways we have not anticipated, we cannot rule out. What the contamination problem ultimately reveals is a two-directional impossibility that does not yield to engineering. We may have already corrupted the experiment we went to run. We cannot maintain biological isolation while also doing the work of surviving. And the mission that most clearly demonstrates the scale of the challenge, returning a few tubes of Martian soil safely to Earth, will not be complete until the 2030s at the earliest. The sample return mission is not a footnote. It is a proof of how seriously the return problem must be taken. And returning soil from an uninhabited planet is the simplest version of the problem. The hardest version involves returning humans who have been living inside that planet's environment for years, carrying everything Mars gave them, back to a biosphere that has no immunity to whatever they bring. That version of the problem does not yet have a solution. And it is not the only thing waiting on the other side of a successful landing. If returning soil from an uninhabited planet requires billions of dollars and years of preparation, and a dedicated containment facility built before the first sample arrives, it is worth asking a harder question. What does a person cost? Not the engineering, not the mission architecture, the whole thing, from first dollar to last. The Apollo program gives us a benchmark. In today's money, it costs roughly $280 billion. That bought 12 people on the lunar surface for a combined total of about 80 hours. 80 hours. A long weekend. The cost per hour of human presence on the moon, adjusted for today's economy, works out to something approaching $3.5 billion per hour of surface time. Mars would not improve that ratio. Conservative estimates put the first crewed Mars mission at somewhere between $500 billion and $1 trillion. That is for a single mission. Not a colony, not infrastructure. One trip, there and back. Creating anything approaching a self-sustaining colony would cost tens of trillions of dollars over decades. The numbers are almost too large to reason about clearly, which is part of why they rarely appear in the same sentence as specific consequences. SpaceX has argued it can change this. Their most optimistic projection puts a Mars ticket at $500,000 per person. But that figure covers transportation only. It excludes habitat. It excludes life support. It excludes food, water, radiation shielding, medical equipment, and the years of resupply missions that any colony would require to survive. The ticket price is the smallest item on the bill. Mars colonization would be the most expensive undertaking in human history. Not one of the most expensive. The most expensive. Here's where the arithmetic becomes uncomfortable. Proponents of colonization often argue that the investment pays for itself. Mars is rich in minerals, the argument goes. Scientific discoveries will transform our understanding. And someday, even tourism. These arguments share a common flaw. They ignore what it costs to move an object between Earth and Mars. Sending a kilogram of anything to Mars currently costs around $10,000. That is a kilogram. A small bag of flour, a laptop. That cost reflects the fuel, the engineering, the launch infrastructure, and the physics of climbing out of 2 gravity wells and crossing hundreds of millions of kilometers of interplanetary space. The cost applies in both directions. Getting something back from Mars costs at least as much. There is no mineral on Mars valuable enough to survive that math. Not one. A kilogram of platinum on Earth is worth roughly $30,000. After transport costs from Mars, it would cost $10,000 just to deliver it, before extraction, processing, refinement, or any infrastructure. Gold, rare earth elements, anything you can name collapses under the same arithmetic. The idea that Mars will become economically profitable is not a bold vision waiting to be realized. It is fantasy economics that ignores basic math. Asteroid mining, often cited alongside Mars as a future resource frontier, at least has a clearer geometric logic. Asteroids are accessible without landing on and launching off a planetary surface. Even asteroid mining remains economically unproven. Mars is harder in every dimension. The science argument fares no better. This is the uncomfortable truth that rarely appears in colonization advocacy. Robots do Mars science better than humans. Significantly better at a fraction of the cost. Rovers do not need life support. They do not need pressurized habitats, or food, or water, or medical facilities. They do not experience radiation anxiety or psychological breakdown or microbiome collapse. They can be designed for specific tasks, deployed continuously, and operated remotely with nothing more than the communication delay we already manage. The scientific return from Mars rovers has been extraordinary by any measure. Curiosity has been operating since 2012. Perseverance has been caching samples since 2021. They have operated for years on budgets that represent a small fraction of what a crewed mission would cost. Adding humans to a Mars science program does not multiply the science. It actually reduces scientific productivity. The reason is simple. The overwhelming majority of a crewed Mars mission's resources go toward keeping the humans alive. Life support, food production, water recycling, medical capability, psychological support, radiation management. Every gram of payload capacity, every kilowatt of power, every hour of crew time that goes into survival is a gram, a kilowatt, and an hour not spent on science. A human crew on Mars would be spending most of its time maintaining the systems that allow them to continue existing, not studying the planet. If the goal is science, robots are the better answer. They already are. The science argument does not justify the cost. It undermines it, which leaves a question sitting quietly at the center of the whole enterprise. If the economics do not work and the science does not require it, what is the human Mars plan actually for? There is an answer to that question, and it is worth examining honestly. The recent push for Mars colonization has been driven in significant part by a small number of extraordinarily wealthy individuals. The vision they describe is compelling. Humanity as a multi-planetary species, a backup for civilization, an expression of our deepest exploratory instincts. These are not trivial ideas, but there is an asymmetry in the vision that deserves attention. The people selling the dream of Mars colonization will not be the ones going. They will not be the ones living for years in a pressurized habitat while radiation quietly damages their neurons, while their bones slowly remodel away from Earth compatibility, while they manage psychological fracture in a sealed container with no escape. The engineers and scientists and mission specialists who actually go will experience all of that. They will pay for the vision with their bodies and potentially their lives, and in some cases their ability to ever return to the world they came from. The people funding the dream will watch from Earth. The most honest framing may be this: the trillions of dollars that a self-sustaining Mars colony would require represent a choice. That same investment could provide clean water to every human being on Earth who currently lacks it. It could end malnutrition. It could fund the research needed to address multiple diseases that currently kill millions of people per year. It could build the climate infrastructure needed to make Earth survivable for the billions of people who will face displacement as the planet warms. These are not abstract priorities competing against an abstract vision. They are specific, solvable problems waiting for resources that exist. Instead, the conversation is about sending a small number of people to a frozen, irradiated desert that already tried to be a planet and failed. That is not a failure of vision. It is a question about where vision is being directed. The economics of Mars colonization require perpetual subsidy from Earth with no plausible return. The robots do the science better and more cheaply, and the resources the dream demands are not unclaimed. They already belong to problems here. But the economic case, as settled as its arithmetic appears, is only the most recent layer of the argument. Underneath it is a question the colonization movement has not resolved, and it is the one that may ultimately matter most. The question underneath the economics is this: could a colony ever stop needing Earth at all? Could it learn to make what it needs, repair what breaks, grow what it eats, and generate its own power? The colonization movement has an answer ready: in situ resource utilization, manufacturing on Mars, self-sufficiency through ingenuity. It is worth following that promise all the way down. The problem begins with something the source calls the fractal manufacturing problem. Every solution creates new problems, and those problems require solutions of their own, and those solutions create further problems in a regress that never reaches a floor. To make concrete on Mars, you need water. The water is frozen and contaminated with perchlorates. To purify it, you need filters. To make filters, you need specialized materials. To produce those materials, you need mining equipment. To build mining equipment, you need refined metals. To refine metals, you need high-temperature furnaces. To power furnaces, you need a massive energy infrastructure. Each step assumes the step before it has already been solved. None of them have. The chain does not terminate. It just keeps going deeper. Advocates usually answer this with 3D printing. Print what you need from local materials. Print spare parts. Print habitat components. Print tools. It sounds like an elegant escape from the supply chain problem. The answer was stranger than expected. Current 3D printers require very specific feedstock: precise plastic filaments, metal powders with exact particle sizes and compositions. You cannot shovel Martian regolith, the loose surface material, into a printer and receive useful objects. The feedstock itself requires an entire chemical processing industry to produce from raw Martian materials. And the list of things you cannot print at all is exactly the list of things a colony most needs. You cannot 3D print electronics. You cannot print seals. You cannot print lubricants. You cannot print complex alloys. The machines most critical to survival fall entirely outside what the technology can produce. And then there is the deeper problem. The printers themselves have hundreds of precision components: nozzles, drive mechanisms, heating elements, sensors. Every one of those components wears out. When your 3D printer breaks, you cannot 3D print its replacement parts, not the ones that matter. You need a printer to fix the printer, and that printer needs fixing too. It is a circular dependency that marketing demonstrations never address. Metallurgy took humanity thousands of years to develop on Earth, with breathable air, abundant resources, and no suits. The idea of replicating it on Mars, in pressure suits with limited tools, starting from frozen contaminated rock, is not an engineering challenge waiting for a clever solution. It is an impossibility. The complexity spiral extends further still. Consider a computer chip. To manufacture one, you need ultra-pure silicon and rare earth elements. You need fabrication facilities that cost billions of dollars to build on Earth. To build those facilities, you need precision machinery. To make that machinery, you need specialized alloys. To produce those alloys, you need a metallurgical industry operating at industrial scale. On Earth, a single electronic component moves through supply chains spanning dozens of countries, hundreds of companies, and thousands of workers before it reaches the device that uses it. A colony of a few dozen people cannot replicate that. Mars lacks rare earth elements in accessible concentrations. It lacks the specific alloys. It lacks the countless specialized chemicals that modern manufacturing requires at every step. Every missing material means one of two things: import it from Earth, which defeats self-sufficiency, or substitute something inferior, which compromises safety in an environment where compromised safety kills. The spare parts crisis makes the arithmetic concrete. A modern pressurized habitat requires thousands of specialized components: seals, bearings, valves, sensors, filters, electronics. Each has its own lifespan and its own failure signature. The source claims that statistical analysis of component failure rates shows a 100-person colony would need millions of spare parts just to maintain basic life support for 50 years. That claim comes without a named source, and the precise number should be held lightly. but the shape of it is right. The diversity of component types alone, each with a different failure rate, makes the inventory problem enormous. And missing even one critical type does not mean inconvenience. It means cascade. The mining equipment problem closes the loop on self-sufficiency completely. To extract raw materials from Mars, you need excavators, crushers, haulers, and processing equipment. That machinery requires hydraulic fluids. On Mars, those fluids freeze. It requires lubricants. In low pressure, those lubricants evaporate. It requires seals. In extreme cold, seals become brittle and crack. Metal itself becomes brittle in the cold. Dust clogs every moving part. Equipment that would last decades on Earth would fail in months on Mars. And when it fails, there are no replacement parts coming. To keep the mining equipment running, you need more specialized equipment, which needs maintenance, which requires supply chains, which requires more mining. It is a recursive loop with no exit. Power is where the constraints converge most dangerously. Solar panels on Mars receive only 43% of the energy they would on Earth. That alone makes solar marginal for the scale of power a colony requires. Heating habitats through the Martian night, running life support continuously, powering greenhouses, operating manufacturing, producing return fuel, which requires enormous amounts of energy in itself. The load is relentless and massive. But the deeper problem with solar is not the reduced baseline. It is the 2018 global dust storm. That storm lasted over 3 months. It reduced sunlight reaching the surface to roughly 1% of normal, blocking 99% of incoming solar energy. Opportunity, the rover operating at the time, fell silent and never woke up. A human colony running on solar power during that storm would simply have died. Not struggled, not adapted. Died. Within days of the power failing, in the cold and dark. Nuclear power seems like the obvious answer. It is. But it creates a new set of problems that do not yield to easy solutions. Transporting enriched uranium or plutonium through Earth's atmosphere means that a launch failure does not just destroy the mission. It risks scattering radioactive material across a wide area of Earth. You need nuclear engineers on Mars to operate and maintain the reactors. Specialists who must be trained, transported, housed, and kept alive. Nuclear waste cannot simply be buried on Mars the way it is managed on Earth, because the geology is unknown and the inhabited surface area is extremely limited. A nuclear accident could contaminate one of the few zones suitable for a habitat, potentially permanently. And reactors require cooling. On Earth, cooling is handled by water or atmosphere. On Mars, water is precious and the thin atmosphere cannot effectively remove heat at the required rate. Power storage compounds everything. Solar only works by day. Mars nights are long and brutal. Batteries degrade rapidly in extreme cold. Temperature cycles cause expansion and contraction that cracks connections and destroys components over time. Chemical batteries lose capacity. Mechanical storage using flywheels requires perfect vacuum seals that degrade. Fuel cells require water that a colony cannot spare. There is no clean solution. Nuclear appears to be the only option that can sustain a colony through a 3-month dust storm. And that means a single reactor failure is not an engineering inconvenience. It is the end. The colony freezes to death in the dark. And none of these systems exist in isolation. Every system in a Mars colony must work in harmony, simultaneously, without interruption. Life support, power, water recycling, temperature control, communication. When one degrades, it stresses the others. If water recycling efficiency drops even slightly, more power is needed to compensate for the loss. That power draw strains the energy system. Less energy available for heating means lower temperatures in the habitat. Lower temperatures stress seals and batteries, causing more failures. Each problem multiplies. On Earth, cascades like this are broken by redundancy, by supply chains, by the ability to call in additional resources. On Mars, the cascade has nothing to stop it. One system's slow degradation can pull the entire colony down with it. Communication infrastructure sits at the edge of all of this, often overlooked. Maintaining contact with Earth requires relay satellites in Mars orbit, for periods when Mars is on the far side of the Sun and direct contact is blocked. It requires additional satellites to connect surface locations to each other. And it requires redundancy, because a communication failure on Mars does not mean a frustrating service outage. It means being entirely cut off from Earth for potentially years. Building and maintaining that satellite infrastructure means dozens of launches and constant replacement as components fail in the radiation environment. Every piece of it must be designed, built, launched, and sustained from Earth indefinitely. Self-sufficiency was supposed to be the answer to the economic problem. It turns out to be another version of the same problem. The colony cannot make what it needs. It cannot fix what breaks. Its power systems are either insufficient or dangerous. Its cascades have no circuit breakers. And so the permanent dependency on Earth is not just financial, it is industrial, mechanical, and existential. Manufacturing on Mars does not escape the regress. It extends it. The industrial impossibility does not stand alone either. It connects directly to a failure mode that combines everything into something more total than any single problem has yet managed to suggest. A settlement that cannot make its own air is a settlement where someone else owns the air. That fact has consequences no treaty currently addresses. The Outer Space Treaty of 1967 is the foundational document of international space law. It prohibits any nation from claiming sovereignty over the Moon, Mars, or any other celestial body. It was written in the early years of the space race, when governments were the only actors capable of reaching space, and when the principal concern was preventing one superpower from planting a flag and declaring ownership. The treaty solved that problem, but it left something else almost entirely unaddressed. It never clearly established what law applies inside a privately operated habitat on Mars who investigates crimes committed there, or what authority a company holds over the people living under its roof. Here is what that gap actually means in practice. If a private company establishes the first Mars base, that company does not own Mars in the formal sense the treaty prohibits. But it owns the habitat. It owns the air recyclers. It owns the water processing equipment. It owns the food supply and the fuel reserves and the communication equipment. Every system that keeps the colonists alive belongs to the company. And the colonists, who arrived on company spacecraft at enormous cost, almost certainly cannot afford the return ticket. The Outer Space Treaty says no nation owns Mars. It says nothing about what happens when a corporation owns everything a person needs to survive. History has a name for this arrangement: the company town. In the industrial era, workers in remote mining and manufacturing operations often lived in housing owned by their employer, bought food from company stores, and could not leave because they owed more than they earned. The geographic isolation enforced the dependency. The economics did the rest. Mars would be a company town on a scale no industrial era coal town ever approached. Not an unpleasant working arrangement. Not an inconvenient power imbalance. A situation in which the company controls the air supply. Where dissent could be punished not with a demotion, but with reduced rations or reassignment to the most dangerous surface work. Where leaving is not an option, because leaving means waiting for a launch window that comes every 26 months, paying for passage on a vessel the company controls, and surviving a 9-month transit on a body already compromised by years of Martian gravity and radiation. The isolation that made industrial company towns exploitative would be multiplied by the distance between planets. Then, the data shifted. Even if the company were entirely benevolent, the structure of the colony would still push toward authoritarianism. Isolated communities under survival pressure do not tend toward democracy. They tend toward hierarchy. Researchers studying extreme environments, including Antarctic stations, submarines, and remote postings, consistently find that small groups under sustained stress develop rigid chains of command, resource hoarding, and sharp divisions between in-group and out-group. These are not failures of character. They are predictable responses to conditions where a wrong decision can kill everyone. The colony leadership on Mars would hold literal life and death authority. They would control who works where, who receives what resources, and who gets access to the medical equipment. Democracy requires freedom of movement and freedom of association. On Mars, leaving the group means stepping outside without a suit. There is no freedom of exit. There is no opposition party. There is no appeal to a higher authority. There is no way to separate from someone whose decisions you find intolerable. Mars colonies would not become dictatorships because the founders wanted that. They would become dictatorships because the environment makes anything else structurally impossible. The legal vacuum compounds every version of this problem. Think about something as concrete as a serious crime. If someone commits murder inside a Mars habitat, who investigates? Under what legal code? A private company from the United States might argue US law applies to its employees, but colonists from other nations would be subject to different national laws. The Outer Space Treaty provides almost no guidance on jurisdiction and enforcement. A colony would need investigators, judges, and detention facilities. It would need legal infrastructure that consumes resources the colony can barely afford to allocate to survival. But without that infrastructure, disputes escalate. Unresolved grievances in a sealed habitat with no exit become something far more dangerous than they would anywhere on Earth. The first serious crime on Mars would create a constitutional crisis with no clear mechanism for resolution. And then, the competitive pressure begins. If one nation or company establishes a successful Mars presence, others will feel compelled to follow. Not because Mars is strategically essential, because the perception of being left behind in a historic endeavor carries political and economic weight that is difficult to resist. The Antarctic Treaty has kept that continent largely peaceful and scientific since 1959. It works because Antarctica has no permanent human population, no commercial extraction of resources, and a network of signatory nations willing to enforce its terms. Mars would face conditions the Antarctic Treaty was never designed to address: commercial interests, permanent settlements, competing jurisdictions, and an enforcement mechanism that would need to operate across hundreds of millions of kilometers with no rapid response capability. The treaty framework is already under pressure from resource extraction interests in Antarctica. A Mars colony would place that framework under pressures of an entirely different order. There are also questions that do not resolve into policy debates. They stay open in a more fundamental way. If Mars has indigenous microbial life, even organisms with no nervous system, no behavior, no recognizable complexity, do they have a right to exist without interference? The question might sound philosophical, but it has direct implications for mission planning, for public support, and for the long-term ethical standing of anyone who establishes a colony on a world they did not examine carefully enough before settling. We already know Mars has seasonal methane releases that suggest something active is occurring beneath the surface. We do not know whether that something is geological or biological. Introducing a human colony before that question is answered would mean potentially ending a biological lineage that predates complex life on Earth without ever knowing it existed. That is a decision that cannot be undone. The sovereignty vacuum, the company-town dynamic, the legal impossibility of governing crime and dissent, the slide toward authoritarianism, the competitive colonial race, and the ethical questions about what we might be overwriting. None of these are arguments for abandoning curiosity about Mars, but they are arguments against the idea that a Mars colony would be a fresh start, a blank slate, a new chapter unburdened by the failures of human history. What the structure of a Mars colony actually suggests is something older, a place where power flows entirely to whoever controls the essential resources, where the people doing the most dangerous work have the least ability to leave, where the laws that protect human beings on Earth simply do not reach. The problems that have followed human civilization everywhere it has gone would follow it to Mars, not in spite of the conditions there, because of them. All of that concerns the people who chose to go. Every risk examined so far, every system failure catalogued, every psychological burden mapped, belongs to adults who made a decision. Volunteers who signed a document and understood, at least in the abstract, what they were agreeing to. A colony is not an outpost. An outpost is a place where people work. A colony is a place where children are born, and that is where the deepest impossibility lives. Think about what a colony actually requires. It requires a second generation. Every human settlement in history, from the first camps on the Eurasian steppe to the first towns on the coast of a new continent, persisted because people had children there. Children who grew up, had more children, and built a civilization that outlasted their parents. That is not one feature of a colony. It is the precondition of everything else. But something was wrong. We have never observed mammalian conception, pregnancy, or birth in reduced gravity. Not once. We have never even attempted it in a controlled scientific setting. No mammal has ever been conceived and carried to term anywhere except Earth's gravitational field. The research gap is not a matter of missing a few data points. It is total. What we do have are mouse experiments conducted aboard the International Space Station. The results were not encouraging. The embryos showed abnormal development. Mortality rates were high. The conditions aboard the station, it should be noted, were microgravity, not the partial gravity of Mars. But that distinction provides less comfort than it might seem. We do not know the minimum gravitational threshold for healthy mammalian development. We do not know whether Mars, at roughly a third of Earth's gravity, clears that threshold or falls below it. We are not extrapolating from incomplete data. We are extrapolating from essentially no data at all. Human fetal development is a process that depends on gravity in ways we are only beginning to understand. Bone forms in response to mechanical loading. The vestibular system, the inner ear network that gives us our sense of balance and spatial orientation, calibrates itself during development. The cardiovascular system learns how hard to pump blood, partly by experiencing the gravitational demand that blood will face throughout a lifetime. All of those developmental processes evolved under one gravitational field, Earth's. Reduce that field by 2/3, and the consequences for a developing fetus are genuinely unknown. A child born on Mars might survive. They might grow up functional, healthy by Martian standards, adapted to the world they were born into. But their heart would be calibrated for Mars. Their bones would be shaped for Mars. Their cardiovascular system would have spent its entire developmental window preparing to pump blood against a gravitational pull 1/3 the strength of Earth's. Return that child to Earth and their own body might become the danger. Their heart, too weak to push blood upward against full gravity. Their bones, structured for lighter loads, potentially fracturing under their own weight. We would have created, without intending to, a permanent underclass of humans who are prisoners of Mars's weak gravity. People who cannot visit the planet their species came from. People for whom Earth is not a home waiting to be returned to, but a place physically barred from them. Not by law, by biology. And that is only the biological uncertainty. The radiation makes everything worse. Radiation exposure during pregnancy causes mutations. Sustained, high-energy cosmic ray bombardment affecting a developing fetus is not a theoretical risk. It is a chemical certainty. The DNA being replicated at extraordinary speed during fetal development is precisely the kind of target that radiation damages most efficiently. Birth defects would not be an occasional tragedy. They would be a systematic outcome. We would not be giving children a difficult life on a harsh world. We would be creating a generation of children whose bodies were damaged before they took their first breath. The medical infrastructure problem compounds this. Preeclampsia, breech presentation, hemorrhage. Any of those obstetric emergencies, ordinary and manageable in any well-equipped Earth hospital, would likely be fatal on Mars. For the mother, for the child, both. The surgical precision that makes childbirth survivable in complicated cases requires not just skill, but equipment, blood supply, specialist knowledge, and the ability to escalate when the first intervention fails. A crew of 4 to 6 people operating in a sealed habitat cannot provide those things. So reproduction itself may be biologically impossible. Or it may be possible only at a cost that produces damaged children. Or it may be possible but fatal when anything goes wrong. Any of those outcomes makes a colony a one-generation dead end. But assume for a moment that healthy births are possible. Assume children survive, develop normally, grow up functional on Mars. The colony still faces a problem that mathematics makes inescapable. A genetically stable human population requires diversity, not for abstract evolutionary reasons, but for immediate practical ones. In small populations, harmful recessive genes, the genes that remain invisible when only one copy is present, become common through random chance. Genetic drift is the term for this process. It needs no bad luck, no radiation, no environmental stress. It happens simply because a small group cannot maintain the genetic variation that a large one can. Within a few generations, those recessive genes begin appearing in their active form. Genetic disorders rise. The population becomes increasingly vulnerable. Studies of population genetics suggest that a truly stable human population requires at least 10,000 people. Some researchers argue that careful management could sustain a viable population with as few as 160 individuals, but that lower number carries a hidden requirement: controlling breeding, deciding who can reproduce with whom, enforcing those decisions. A scientific program of managed human reproduction is not a euphemism for anything mild. It is a eugenic program. A small colony faces the choice between genetic collapse on one side and reproductive tyranny on the other. There is no third option that the math provides. And it is not only human reproduction that fails. A colony needs more than people having children. It needs a functioning ecosystem. Bacteria that break down waste, fungi that decompose organic matter, insects that pollinate crops, microorganisms that make soil productive. Every plant the colonists grow depends on a web of microbial relationships that we understand in general terms, but not in Martian terms. The nitrogen-fixing bacteria that convert atmospheric nitrogen into a form plants can absorb may not function in Martian gravity. The gut bacteria colonists carry, the microorganisms that allow them to digest food and regulate their immune systems, may mutate or die under sustained radiation bombardment. We do not know. We genuinely do not know. And that uncertainty is not a gap that engineering fills. It is a biological mystery that only biology can resolve. The pressure to resolve it through genetic modification would become intense. If colonists cannot reproduce safely, engineer radiation resistance. If their children develop incorrectly in low gravity, engineer physiological adaptations. If the gut microbiome collapses, engineer tolerance for different biological support systems. The logic is compelling. The consequence is not. Genetically engineering humans to survive on Mars means creating humans who are not quite the same species as the ones on Earth. Not in metaphor. Literally. Reproductive compatibility between populations depends on shared genetic architecture. Alter that architecture substantially and interbreeding becomes impossible. The colonists and their descendants would drift apart from Earth humans not just culturally, not just psychologically, but genetically. A new branch of humanity. One that could not return to its origin. One that, over generations, might not even recognize Earth humans as the same kind of being. Natural selection would push the same direction without any deliberate engineering. High radiation and low gravity favor different traits than Earth does. Individuals who tolerate radiation better, whose cardiovascular systems are more efficient at lower gravitational demands, would survive and reproduce at higher rates. Over centuries, the Martian population would evolve away from the Earth population. Not quickly by evolutionary standards, but in the context of a civilization maintaining contact across interplanetary distances, the divergence would be real, and it would deepen with every generation. We are not spreading humanity to the stars. We are fracturing it into fragments that may never fully reconnect. Some people argue that life's adaptability answers this. Extremophiles, organisms that thrive in conditions once considered completely uninhabitable, near hydrothermal vents, in hypersaline lakes, deep in Antarctic ice sheets, are offered as proof that life finds a way. If bacteria can survive in boiling acid, surely humans can adapt to Mars. But this misses the point entirely. Those organisms did not choose Mars's conditions. They evolved over billions of years, through billions of generations of selection, to handle one specific extreme environment. The bacteria near a hydrothermal vent did not arrive there and adapt. They are the survivors of a process that took longer than complex animal life has existed. Humans cannot evolve that way. Not in decades, not in centuries, not in millennia. Genetic engineering is powerful, but it cannot compress billions of years of evolutionary refinement into a laboratory process. We are not extremophiles. We are fragile organisms whose survival depends on an extremely narrow range of conditions. Mars does not sit outside our comfort zone. It sits outside our survival zone entirely. But there is a question that sits underneath all of this. Underneath the biology, the genetics, the ecosystem failure, the evolutionary divergence. A question that is not scientific. A child born on Mars did not choose to be born there. They did not evaluate the radiation exposure, the gravity deficit, the genetic bottleneck, the medical limitations, and decide that the trade-off was acceptable. They arrived in a sealed habitat with recycled air, unable to leave it without a suit, on a planet where they will never swim in an ocean, never climb a tree, never feel rain on their face, never breathe unfiltered air. Not as a sacrifice they made, as the only life they were given. Studies of children raised in severely restricted environments show consistent and serious outcomes. Developmental delays, social dysfunction, difficulty forming normal human relationships, mental illness at rates far above those of children raised in ordinary circumstances. A colony on Mars could not provide diverse social interaction. It could not provide meaningful exposure to nature. It could not provide the educational and developmental breadth that children require not just to flourish, but to develop into psychologically healthy adults. The children of a Martian colony would face those deprivations from birth, with no possibility of remedy. The question of whether it is ethical to bring children into that existence is not a rhetorical one. It is the moral center of the entire colonization argument. Because a colony that cannot raise a healthy second generation is not a colony. It is a slow extinction with a settlement's name attached to it. And if reproduction is the precondition of everything, then this may be the impossibility that contains all the others. There is one answer left. It is the largest answer anyone has proposed. It is the answer that makes all the other problems dissolve, that makes the radiation and the dust and the psychology and the food shortages feel like engineering challenges rather than permanent walls. The answer is that we would not have to live inside sealed boxes at all. We would remake the planet itself. We would terraform Mars, transforming a frozen, irradiated desert into a second Earth, with a breathable atmosphere, liquid water on the surface, and a sky that turns blue at noon. It is worth doing the arithmetic on that idea before we accept it. The vision goes like this. We release greenhouse gases into the Martian atmosphere, triggering a warming cycle. We melt the polar ice caps. We thicken the air gradually until the pressure rises enough to support liquid water. Over centuries, perhaps millennia, Mars becomes hospitable. It is a compelling picture. And the first thing the arithmetic destroys is the atmosphere itself. Mars has about 1% of Earth's atmospheric pressure. To make it breathable, we would need to increase that pressure by at least 50 times. The most accessible source of atmospheric material on Mars is carbon dioxide, locked in the polar caps and absorbed into surface rocks. Scientists have estimated the total available CO2 across the entire planet. Every gram of it. Polar caps, regolith, bedrock. If we released all of it at once, every molecule, we would produce an atmosphere roughly 7% as thick as Earth's. Not 50 times thicker. 7%. Still far too thin to breathe. Still far too thin to warm the planet significantly. The total CO2 inventory of Mars is not enough to terraform Mars. Not even close. That is the first wall. Here is the second. Even if we somehow thicken the atmosphere, it would not stay. Mars lost its original atmosphere billions of years ago, and it lost it for a specific reason. The planet's core cooled and largely solidified. Without a churning molten iron core, Mars lost the convective motion that generates a global magnetic field. Without a magnetic field, the solar wind, a constant stream of charged particles pouring outward from the sun, struck the upper atmosphere directly and gradually stripped it away. That process is not historical. It is ongoing. Any atmosphere we rebuilt would face the same stripping. We would be filling a bucket with a hole in it. The proposed solution to the magnetic field problem is an artificial one. Scientists have suggested placing a powerful magnetic field generator at the Mars-Sun L1 point, a gravitationally stable position between the two bodies where a satellite can hold its position indefinitely. The generator would cast a magnetic shadow over Mars, deflecting the solar wind. It is technically coherent as an idea, but the generator required to produce a planetary-scale magnetic field would need to be the size of a small moon. The energy requirements alone are beyond anything humanity has ever contemplated. Maintaining it forever without failure, with no possibility of a resupply window missed, or a component degraded, is a constraint no engineering system we have ever built has met. Creating a planetary magnetic field might as well be magic. That is not hyperbole. It is an accurate description of the distance between what we can build and what the problem requires. And the timeline, even in the most optimistic scenario, would stretch across tens of thousands of years for minimal atmospheric thickening. Importing gases from elsewhere in the solar system, the only way to supplement Mars's insufficient CO2 inventory, would take millions of years with any technology we can conceive of today. Terraforming is not a long-term plan. It is a geological event masquerading as an engineering project. The picture did not hold. We are discussing the possibility of engineering another planet's entire biosphere, while we are actively failing to manage the biosphere we already have. Earth's atmosphere, its water cycle, its climate system, its soil ecosystems, took billions of years to assemble. It is by any measure perfect for us. And we are degrading it measurably year by year, despite knowing exactly what we are doing, and despite having every incentive to stop. The idea that the same species will terraform Mars is, the source material does not exaggerate here, perhaps the height of human hubris. We cannot manage one planet's climate. We believe we can engineer another planet's entire biosphere from scratch. So terraforming is not the long-term answer. Mars stays Mars. And Mars, as it is, has problems we have not finished counting. The InSight lander, NASA's geophysical probe that operated on the Martian surface until late 2022, detected Marsquakes. Mars is still geologically active. These are not like earthquakes, which are generated by tectonic plates grinding against each other in patterns that, while unpredictable at the exact moment, follow understood fault lines. Marsquakes arise from a different mechanism, thermal contraction of the cooling crust, and their patterns and triggers are not yet understood. A Marsquake strong enough to crack a habitat seal would be catastrophic with no warning and no predictable probability model to plan around. Ground-penetrating radar surveys of the Martian surface have revealed something more complicated. Extensive underground cave systems and lava tubes run beneath large portions of Mars. At first hearing, this sounds like an answer. Ready-made shelters, already underground, already protected from radiation. But the caves are geological unknowns. We do not know if they are structurally stable. We do not know what gases fill them, whether residual volcanic outgassing has left pockets of toxic chemistry, or whether the rock chemistry itself interacts dangerously with human biology. Exploring them would be incredibly dangerous. Sending people into geological unknowns on a planet where evacuation is impossible, and medical infrastructure is a trauma kit, and a general practitioner is a risk that could end the mission instantly. Not exploring them, though, may be equally fatal. They may represent the only viable habitat option on the surface, the only place where radiation shielding is naturally provided and construction requirements are manageable. A catch-22 with mortal stakes on both sides. And above the surface, the asteroid risk is higher on Mars than on Earth. Mars sits closer to the asteroid belt. Its thin atmosphere, the same atmosphere that fails as a radiation shield and fails as a pressure source, also fails as a meteor shield. Earth's thick atmosphere burns up the vast majority of incoming small impactors before they reach the ground. Mars has no such protection. Without a thick atmosphere to ablate incoming objects, even relatively small impacts could destroy a surface installation completely. Early warning systems for Mars are not developed. There is no deflection capability. There is no evacuation. Colonists would live with the permanent possibility of instant annihilation from above, with no recourse at any stage. Now consider the timeline. Optimists place Mars colonies in the 2030s or 2040s. Every major space project in history has taken longer than predicted. The James Webb Space Telescope was planned for a 2007 launch. It launched in 2021, 14 years late. The International Space Station was planned for completion in the 1990s. It was not finished until 2011. A Mars colony is not more complex than the Webb Telescope or the ISS in the way that a larger project is more complex than a smaller one. It is exponentially more complex, in a different category entirely. Even with a dedicated program and effectively unlimited funding, a realistic timeline puts a first crewed landing in the 2040s, and anything resembling a permanent base in the 2060s or 2070s. By the 2060s, climate change will have transformed Earth in ways we are only beginning to model. Artificial intelligence will have restructured every sector of human civilization. We may have technologies that render the entire rationale for Mars colonization obsolete, or we may have problems so acute that the resources required for Mars are simply unavailable. We are planning for a specific future using today's assumptions. The future never arrives as expected. It never has once. The arithmetic is complete. Terraforming requires resources and timescales that place it outside the category of plans. The geological environment is active, unknowable, and lethal from multiple directions simultaneously. And the timeline, by every historical precedent, will slip by decades into a world that may no longer resemble the one in which the plan was made. And yet, for all of this, the largest question in the Mars colonization argument may not be whether we can go. It may be what happens to the planet we are leaving behind. Set them side by side and something becomes visible that no single objection could show on its own. The radiation does not wait for the bone loss to finish before it starts destroying neurons. The bone loss does not pause while the microbiome collapses. The psychological breakdown does not hold off until the dust has finished accumulating in the lungs. Every system fails at the same time, and as each one fails, it makes every other failure worse. A colonist struggling with cognitive decline from radiation damage is less capable of maintaining the water recycler. A colonist with weakened bones and reduced cardiovascular output is less capable of the physical work that survival demands. A colonist in psychological crisis is less capable of making the careful, methodical decisions that keep a habitat sealed. This is the part that optimistic projections consistently miss. The challenges are not a queue, they are a web. Think about what a colonist's body actually looks like after 5 years on Mars. The radiation has been destroying DNA and brain tissue without interruption since the day of departure. The gravity has been slowly remodeling bones and decalibrating a cardiovascular system that evolved for full Earth weight. Toxic dust has been accumulating in lung tissue with each excursion, each suit entry, each airlock cycle. The microbiome has been degrading under sustained radiation and altered gut chemistry. The immune system has been suppressed for the entire duration, suppressed not for a 6-month ISS tour, but permanently, with no recovery period and no return to Earth for repair. 5 years in, the portrait is not a worn but functioning explorer. The portrait is a person who is cognitively impaired, physically crippled, psychologically broken, and failing across multiple organ systems simultaneously. Not one of those things, all of them, at once. That is not a hard problem with an engineering solution waiting in a research laboratory somewhere. That is a fundamental incompatibility between human biology and what Mars actually is. Here's where the argument deepens past the medical and physical. Earth supports life not merely because it has the right ingredients in the right concentrations. It supports life because of energy flows. Sunlight reaches plants and moves up through animals. Ocean currents carry heat from the equator toward the poles, and cold water from the depths to the surface, distributing energy across the entire planet. Geological processes melt rock, release minerals, recycle carbon, and circulate nutrients through soil and ocean over millions of years. Life on Earth does not merely exist within these flows, it depends on them structurally, the way a city depends on water pressure in its pipes. Mars has none of them. Not a reduced version, not a weakened version, none. The core froze billions of years ago. Geological recycling effectively stopped. The atmosphere thinned to near nothing. The ocean, if there ever was one, vanished. Mars is not a planet that is struggling to support life. It is a planet that stopped processing energy in the ways life requires. It is thermodynamically dead. Creating artificial energy flows inside a Mars colony would require importing more energy than the colony could ever produce. You would be trying to push water uphill forever. Physically possible in the sense that the laws of physics do not prohibit it, but energetically unsustainable in the sense that the input always exceeds the output, and the gap never closes. Every Mars colony, however well designed, would be an energy sink, a tiny bubble of life in an ocean of death, consuming resources continuously, producing no surplus, dependent on Earth for its survival indefinitely. That is not a frontier. That is a monument to attrition. Something else was happening because the most powerful argument for Mars colonization is not the adventure. It is the insurance policy. The logic goes, Earth is fragile. A nuclear war could make it uninhabitable. A massive asteroid impact could wipe out civilization. A runaway climate catastrophe could render large portions of the surface unlivable. So we need a second home, a backup, a place where humanity survives even if Earth does not. It sounds persuasive. And then you examine what the catastrophes actually do. A nuclear war, even a large one, would be devastating. It would cause mass casualties, regional climate disruption, agricultural failure, and immense suffering. It would not, however, remove Earth's atmosphere. It would not eliminate liquid water. It would not strip away the magnetic field or reduce atmospheric pressure below the threshold at which blood boils. The planet would be deeply damaged. It would still have breathable air. An asteroid impact of the kind that ended the age of the dinosaurs would be catastrophic beyond any historical human experience. It would still leave a planet with gravity, with pressure, with shielded surface conditions, with water. A ruined Earth would be a terrible place to live. It would still be incomparably more hospitable than Mars has ever been in its entire geological history. Wait, the backup planet logic inverts. If you have the technology to build a habitat that keeps people alive on Mars, with its near-vacuum atmosphere, its toxic dust, its constant radiation bombardment, its total absence of life support infrastructure, You already have the technology to keep people alive through any catastrophe Earth could produce. Underground bunkers in Antarctica, as hostile as they sound, would be paradise compared to Mars' surface habitats. You would be standing on a world that still has air, still has protection from radiation, still has water that does not require industrial extraction from frozen toxic regolith. The colony would be a far simpler engineering problem, and it would be starting from a fundamentally more viable baseline. The insurance policy is not insurance at all. It is a solution to a problem that is harder than the original problem. And there is one more dimension to this that rarely receives serious attention. Even if colonists arrived, even if they survived, the civilization they built over generations would not be human civilization in any continuous sense. Language diverges under isolation. A colony of a few hundred people, cut off from the living flow of Earth's languages, would develop its own dialect within decades, and its own distinct language within a few generations. Culture diverges the same way. No new art arriving in real time. No music, no literature, no immigration bringing perspectives from the outside. Historical isolated communities, from island populations to extreme environment outposts, consistently develop rigid hierarchies, intense conservatism, and deep resistance to change. The social architecture of survival under scarcity selects for those patterns. The knowledge base would freeze almost immediately. Earth's databases, journals, technical manuals, and educational infrastructure would be inaccessible in real time from the beginning. The colonists would arrive with a snapshot of human knowledge from their departure year, and that snapshot would begin aging the moment the ship left Earth orbit. Within a generation, they would be a technological backwater frozen in time, working with equipment they increasingly could not repair, using knowledge that Earth had moved beyond. Not slightly out of date, permanently out of date. The idea of maintaining a unified human species across two planets, cooperating, sharing knowledge, building on each other's progress, is not merely optimistic. It is a misreading of what isolation does to human communities. We cannot maintain unity on one planet. The suggestion that we will manage it across a communication gap measured in minutes and a physical gap measured in years strains the argument past breaking. What we are describing, if we follow the evidence honestly, is not colonization. It is not a backup. It is not an insurance policy. It is a small group of people sent to a place that is incompatible with human biology, sustained at enormous cost by a civilization they would increasingly diverge from, failing across every system simultaneously, unable to reproduce sustainably, unable to return, unable to receive real-time help, building something that calls itself humanity's future, while spending that future one slow year at a time. The web holds, every thread connects, and none of them lead to Mars as a second home. What they may lead to is a different question entirely, and a harder one. That question, the one left hanging at the end of all that evidence, is harder than any of the engineering problems. It is this: if we cannot survive on Mars, the most Earth-like planet in our solar system, then what does that mean about everywhere else? It means we are alone. Not probably alone. Not alone for now. Alone in a way that the universe has made structural. The universe is not hostile to life. That would almost be comforting. Hostility implies intention. The universe is indifferent to life. Earth is where life happened to work. The product of a specific star, a specific distance, a specific chemical accident repeated across billions of years in exactly the right gravitational field with exactly the right shielding overhead. Mars is not Earth's twin that drifted away. Mars is the evidence that even next door, in the same solar system, under the same sun, the conditions for life are nearly impossible to meet. If we cannot cross that gap, the universe beyond is not a frontier. It is a wall. This is not defeatism. It is something more valuable than optimism. It is clarity. The ambition that drove us here was never wrong. The instinct to reach, to explore, to cross the next horizon. That instinct built boats and mapped coastlines and put 12 human beings on the surface of the moon. It is one of the finest things about us. That is when the pattern broke. We turned that instinct toward a destination that was never going to receive us. And in doing so, we stopped looking at what was directly behind us. A door closing is not the whole story. What has been behind us the entire time matters more. We have a planet. We have a planet with breathable air maintained by forests and phytoplankton. A planet with liquid water in quantities that would seem miraculous viewed from Mars. A planet with a magnetic field quietly deflecting cosmic radiation, with an atmosphere burning up meteors before they reach the surface, with soil containing more living organisms in a single handful than there are stars in the Milky Way. We have a planet that evolved us, assembled every atom in your body from stellar material over billions of years, calibrated your cardiovascular system and your immune system and your nervous system to its exact gravity, its exact atmospheric pressure, its exact spectral light. You are not on Earth in the way you are inside a building. You are Earth, temporarily organized into human form, assembled by its biosphere and dependent on it in ways that go all the way down to the molecular. Mars was never the next chapter of human history. It was a distraction from writing Earth's next chapter well. And while our attention drifted toward that red light in the sky, the chapter here grew harder to write. Climate change is restructuring the atmospheric systems that regulate temperature and rainfall across the entire planet. Biodiversity collapse is dismantling the ecosystems that produce the food we eat and the oxygen we breathe. Inequality is concentrating the resources needed to respond to both. Pandemic disease has demonstrated in living memory how quickly a single biological event can cascade across a globally connected civilization. These are not abstract problems. They are solvable problems. That is the crucial distinction. They require resources and attention and the kind of sustained engineering ingenuity that, right now, is being directed toward a place where humans cannot live. We are fiddling with Mars while Earth burns. Every dollar spent on Mars colonization infrastructure is a dollar not spent on climate restoration. Every brilliant engineer designing Mars habitat systems could be designing Earth habitat systems, closed-loop food production, water recycling, renewable energy at a scale that transforms how billions of people live. Every launch is not just expensive, it is a choice about where vision is being directed. But here is the turn, and it matters. The technologies are not the error. The destination is the error. The work of learning to close a life support loop, to recycle every gram of water, to live within a fixed energy budget, to grow food in hostile conditions, to build structures that withstand extreme environments, that work is exactly the work Earth needs. We do not need to fly those technologies 225 million kilometers away to apply them. A colony that masters closed-loop life support and brings that knowledge home has done something genuinely useful. A colony that applies those same principles to make a permanent home on Mars has not. The distinction is between a tool and a destination. Accepting Mars's impossibility is not the end of human ambition. It is the redirection of it, not escape from a disposable planet. Stewardship of an irreplaceable one. Not cosmic colonialism, the impulse to consume and move on when the damage is done. Cosmic humility, the recognition that we are creatures of one specific world, extraordinarily lucky to exist on it, and responsible for it in ways we are only beginning to understand. We are not destined to spread across the universe. We are destined to be Earth's caretakers, the only known consciousness in a vast unconscious cosmos, which means the only known thing capable of choosing whether the living world continues. The next time someone describes Mars as humanity's backup planet, consider what that phrase actually requires. It requires believing that a planet with no breathable air, no liquid water, no global magnetic field, no soil, no biological support structure of any kind, at pressures that would kill an unprotected human in under a minute, is a more viable emergency option than a planet that already has all of those things, even in damaged form. A ruined Earth, after any catastrophe we can imagine, is still incomparably more hospitable than Mars has ever been at any point in its geological history. The backup logic does not merely fail, it inverts. Earth is not our first choice, it is our only choice. It always was. The red planet will remain what it has always been, a beautiful light in the night sky, a subject for our robots to explore, a window into the early solar system, and a reminder that in all the vast cosmos, there is no place like home. Carl Sagan saw that from the far edge of the solar system in 1990, when Voyager turned its camera back toward the inner planets, and Earth appeared as a fraction of a single pixel, a pale blue dot suspended in a sunbeam. That, Sagan said, is the only home we have ever known, not a limitation, an invitation. An invitation to bring the same ingenuity, the same courage, the same refusal to accept that problems are permanent. which we were prepared to carry to Mars and turn it toward this world instead. The challenge was never escaping Earth. The challenge is becoming worthy of it.